In this video, we're going to talk about Mask RCNN. Mask RCNN is the extension of the previous work called Faster RCNN, and further improves the region proposal-based convolutional neural network for detection and this time segmentation. The focus of this work is on instance segmentation, and it only adds a small overhead, which is the result of adding a fully convolutional neural network, a small version of it, that helps predicting a mask for the region, for the proposed regions as well. It is almost real-time with a 5 frame per second runtime, and it is very easy to generalize and transfer to other tasks, which in the actual paper they show that the representations learned for this are actually useful for the pose recognition as well. And the focus of this work is on instance segmentation, and it's a simple architecture. A new branch has been added to the Faster RCNN model in order to take care of segmentation mask prediction on regions of interest. It is important to mention that alignment, mainly pixel level alignment, doesn't happen in the Faster RCNN. In the Mask RCNN, the ROI align, which is a simple and quantization-free component, takes care of that. And one thing that it basically shows is that this leads to an improvement in mask accuracy by 10 to 50%. Leading to the conclusion that a stricter localization matrix is actually useful. One thing to note is that in Mask RCNN, classification, meaning detecting to what class a certain element belongs, and the segmentation of it are two independent things, and Mask RCNN decouples them. One important work previous to Mask RCNN was Deep Mask, in which basically there was a segmentation phase which preceded the recognition phase, which was done by the Faster RCNN. In this case, none of them precede the other one, it's just that they are decoupled and there are multiple branches in the actual architecture. This means that you have C different masks predicted by the mask branch, and then the classification branch takes care of classification. And there is no class competition taking place in the mask prediction part. In contrast to a segmentation-focused work, fully convolutional neural networks for segmentations, for semantic segmentation, the objective is to assign a class to each pixel of the image, so you have a per-pixel multi-class categorization. One other thing to note is about the training time of the Mask RCNN, which takes between 1 to 2 days on an 8 GPU machine. Going over the Faster RCNN model, there are two key stages. One is that candidate object bounding boxes are basically created using a region proposal network that takes the image and basically outputs these. The next phase is using the ROI pool on the features of the image in order to obtain features per each one of the candidate object regions. So let's call it F. And then there are two parallel branches, one for basically regressing the bounding box offsets and the other one for classification of the class of that object within the bounding box. In the Mask RCNN, there is going to be a third parallel branch, which is basically responsible for predicting a binary mask per region as well. From each one of the sampled regions of interest, we have 3 loss components contributing to the loss per that region of interest. One of them has to do with the classification, and the other 2 have to do with the mask and the bounding box regression. Having a bounding box or a region of interest of size M and M, and let's say you have K classes, the mask tensor is going to be a KM2 element tensor that basically creates a binary mask for each one of the classes. So it's going to be class 1, class 2, all the way till class K, and each one of these are M by M. Note that if the ROI that you have actually belongs to this class, basically the loss that you have is going to be computed by the contribution of this mask and this mask only, meaning that the other K heads do not really contribute. What this means is that basically you have K, meaning 1 per each class, mask prediction heads that really don't have much to do with the classification. And the loss for mask is basically an average cross-entropy loss. Again, for predicting these masks, they use a small fully convolutional network that has fewer parameters than if they wanted to do with the fully connected networks for mask prediction. And in order to do that, they want the ROI features themselves to be small feature maps. And in order to preserve the per pixel spatial correspondence, they proposed the ROI align layer. What was happening in the ROI pool was that basically you would get a quantized version of the region of interest from float to discrete feature map coordinates, and then you would subdivide it to also spatial bins, and then quantize those bins as well, and then aggregate by max pooling. And the misalignment which is resulting from this is argued in this article to have a negative impact on predicting the masks, while not having a serious impact on the classification prediction, because the classification branch is not really too sensitive regarding translations. In ROI align, there is no quantization, and bilinear interpolation is used instead. So having an ROI, which is not quantized, they have chosen 4 regular locations and then basically used the bilinear interpolation in order to compute the feature values at those regions, and then averaging or maximization can be used in order to obtain the value. They also show that having a single value at each bin can also be nearly as effective. Another thing that they have done is that more than 4 locations per bin seem to diminish the results. MaskRCNN is a framework, and as its backbone, they have investigated the use of ResNet and ResNext with 50 or 101 depths. The convolution layer fourth features have been a common choice for basically using the features. Another backbone choice that they have used is the feature pyramid networks. In the use of FPN, everything is pretty much the same, aside from the fact that different levels of the feature pyramid according to their scale will contribute to the features that you will end up having for each region of interest. For the head branch, they follow the faster RCNN architecture, and they just add a fully convolutional network for mask prediction. As for the training, when you consider each bounding box, the IOU threshold of more than 0.5 is basically determining whether or not that bounding box is a ground truth or not. And the loss of mask prediction is only defined on the ground truth bounding boxes. Images are resized to the shorter edge being 800 pixels. They have the minibyte size of 2 images, and each image has n sampled ROIs, with a ratio of 1 to 3 positive and negative. This n is said to be 64 for the C4 backbone and 512 for the FPN. The training has took place on 8 GPUs, meaning that with the byte size of 2, the effective byte size was 16. And they have trained it for 160,000 iterations, learning rate of 0.02, and decreased by 10 at the 120th iteration with a milestone scheduler. The rate decay of 1e-4 was used, and the momentum of 0.9. During the inference time, they have 300 proposals for the C4 backbone and 1,000 proposals for the feature pyramid network backbone. Non-maximal suppression is performed, and the 100 highest scoring detection boxes will be used in mask prediction. Per each one of these ROIs, K masks is going to be predicted, and from that, the only mask that is going to be used is the kth mask, which is the one that the classifier branch predicts. As for the metrics they have used, on COCO specifically, the average precision, basically the mean average precision over different IOU thresholds have been chosen. There's also AP50 and AP75, and also for different scales of the regions, we have APS, AP medium, and AP large. The first finding is that deeper networks actually have benefits and help improve the performance. One other thing that they have shown is the significant improvement of 24.8 AP to 30.3 AP as a result of decoupling the classification from mask prediction. This has been achieved basically by using a FCN similar loss and basically having softmax and multinomial distribution, while the 30.3 is computed using this decoupled version. They have also shown that these two tasks are to some extent empirically independent, meaning that if you have like a singular class predictor, meaning that instead of predicting k m by m masks, just predicting one m by m without regard to any classes, called class agnostic masks, you would get 29.7 AP. Another thing that they have shown is that the multitask nature of the mask RCNN actually helps improving the box detection as well, such as, for example, if they add the ROI align to the faster RCNN, actually the box detection would go up. However, it still would be lower than the case in which you have the mask RCNN and the multitask nature of box regression and classification, as well as the mask prediction, would actually help refining the representations, therefore resulting in a better box prediction. In transferring the mask RCNN to the task of human pose estimation, they have k masks generated, each corresponding to one of the key point types, for example, left shoulder. And the results indicated the generality of the mask RCNN.